Hello everyone, this is part of a problem-solving series that would help you prepare for math competitions such as the AMC 10 and 12, the AIME, and other contests and tournaments in the advanced middle school and high school level. In this session, we will be solving a number theory problem from the ARML competition. Here's a view of this problem. We would basically like to compute the smallest positive integer n such that n to the power n has at least 1 million positive divisors. So let's assume without loss of generality that n has in fact k distinct prime divisors, and pk, ak, and here obviously we are claiming that a sub I is greater than or equal to 1 for all I, obviously. Okay, and therefore this would imply that n to the power n can simply be written as p1 and a1 times p2 and a2 times all the way to pk and ak. And we would like to count the number of positive divisors. Obviously we know the formula very well. That would be simply equal to na1 plus 1 times na2 plus 1 all the way to nak plus 1. And obviously because each of our ai's are greater than or equal to 1, so this expression is definitely greater than or equal to n plus 1 raised to the kth power. We just realized that it's possible to find an upper bound. Well, consider the case where so we're trying to make this one probably 100, and then this would be the third power, for instance. So if n is equal to 9 is greater than or equal to 99 and k is greater than or equal to 3, in that case that would imply that our the number of divisors of n to the n is obviously going to be greater than or equal to 100 to the third power, which is equal to 1 million. So that would satisfy the conditions of our problem. And sure enough, the number 102, the prime factorization is simply 2 times 3 times 17, and it satisfies these two conditions, and as such we already have a winner here. But is it possible to find a smaller number than 102? So what we want is to look at the cases where actually n is strictly less than 99. So is there any number which would work for the case where n is strictly less than 99? Well, if there is such a thing, that should satisfy at least two conditions. Well, the first condition is we want to have ai's, those powers, to be less than or equal to 6. Even in the case when the prime distinct prime factors, one of them is 2, the smallest possible case, because p to the 7th power, even when p is pretty small, it would be definitely greater than 100, something that we definitely don't want. And the second condition that I would like to impose is that we would like to make k less than or equal to 3. And this is also for a good reason, because, well, obviously if we had 4 distinct prime divisors, these are the last, the smallest 4 that we can think of, it's already more than 100 again, so that would be a violation again. So therefore, given that we have these two conditions, is it possible to find a number n which will be less than 99 actually? Okay, so let's check actually the cases for k. Let's check the case where k is actually equal to 1. Our number has at most one distinct prime factor, but that one is easily ruled out, because in that case d to the power and n is definitely going to be it will be less than or equal to 6 times n plus 1, obviously, and that number is definitely going to be strictly less than 601, something that is totally so we want that number to be more than 1 million, so that case will not work. Another case where k is equal to 2 again we'll create a violation. In that case our number will be less than or equal to 6n plus 1 squared. Still not enough, so that case is also ruled out. So we would like to exclusively focus on the case where k is equal to 3. Our number has 3 distinct prime factors, huh? In that case n can be written as p1 a1, p2 a2, p3 a3. So let's first start with the smallest possible case. Could it be possible that a1 is equal to a2, which is equal to a3, and they're all equal to 1? So that would again create a violation, because when you look at this condition here, this it will immediately tell us that dn to the n will be definitely equal to n plus 1. Each of the ai's here in this is equal to 1, so cubed, and this number is again strictly less than 100 to the power 3, right? Because we already know n is strictly less than 99. As such, this is less than 100 strictly, so that will be a violation again. So that implies that at least one of the powers here is 2, and in that case, when we order the potential cases, we realize there's only 3 possibilities. The answer would be either 60, 84, or 90, because so 60 is simply let me write that down actually. So 2 squared times 3 times 5. 84 is simply 2 squared times 3, that's 12 times 7, so that would give us an 84. And then 90 would be simply 2 times 3 squared times 5, yeah, I believe. Okay, so let's start with the first case. So in this case we have 60 to the power 60. Well, that thing is simply equal to d of, as we mentioned, 2 to the power 120 times 3 to the power 60 times 5 to the power 60, and so that product is 121 times 61 times 61, and that's definitely less than a million. Actually, this turns out to be less than even 800,000, because you can simply replace these numbers with 125, 80, and 80. It's easy to multiply these out. So that case definitely doesn't work. So let's have a look at the second case. So d84 raised to the 84th power. So that would be 2 to the power 1. So this one, again, this is 168. This is 84. This is 84. Now when we multiply the potential product, so 169 times 85 times 85. Now this number is definitely greater than 1 million when you compute it. It's easy to see because this number is definitely greater than 160,000, 160. These two are greater than 80, so you multiply them and you get definitely more than a million. And actually that solves the problem. I don't have to check for this case because this one works, and therefore 84 is the least positive integer n, such that d to the power 84 raised to the 84 power is definitely greater than a million. And so therefore the answer to the problem is 84, and we are done.